We totally take for granted that we can just slice up physical hardware into multiple completely isolated virtual machines. But the mechanics behind this whole process, and honestly where it's all heading, are fundamentally reshaping computing as we know it. So let's dive right into this explainer on virtualization. My name is Hector Wong, and I profess ICS at Leeward Community College. My office is located at the Waianae Moku Satellite Campus. Come visit. At its core, virtualization is basically the engine that decouples our operating systems from the physical hardware. It's the magic that allows Windows, Mac, and Linux environments to run concurrently on a single physical machine, completely isolated, without you having to constantly reboot your system. It's an absolute game changer. And this decoupling, it gives us incredible flexibility. For us, it means developers get these safe, isolated sandboxes to just detonate code without worrying. IT teams can keep those older legacy enterprise apps alive on modern servers. Plus, we get seamless, on-demand, cross-platform execution whenever a specific environment is required. Now, while all of this feels like the absolute bleeding edge backbone of modern cloud computing, here is a wild fact for you. The underlying architecture actually hasn't changed much since 1967. Yeah, 1967, that's when IBM first pioneered this exact same concept on their massive mainframes. So, what's the engine driving this today? Well, we call it the hypervisor. Think of the hypervisor like an incredibly strict traffic cop operating right at the hardware level. It securely rations out your physical CPU cycles, your memory, and network bandwidth just to ensure every single virtual machine stays perfectly separated. But of course, a traffic cop is kind of powerless without the right infrastructure to back them up, right? Modern silicon actually had to evolve specifically for this. We're talking about processor features like Intel's VT or AMDV, which are absolutely crucial to process all that heavy hypervisor lifting efficiently, alongside just massive amounts of RAM. And this hardware evolution gives us two distinct deployment models. First, you have a Type 1 or bare metal hypervisor. This sits directly on the hardware for maximum lean enterprise efficiency. Then you have a Type 2 or hosted hypervisor, which simply rides comfortably right on top of your existing desktop operating system. Now, beyond just CPU and memory, the hypervisor also perfectly controls your networking. It gives you choices. It lets VMs share an internet connection via NAT or bridge directly, so they act exactly like a physical network device on your local network. Or if you need it, they can stay locked down in a totally private internal network for maximum isolation. Okay, but we've got to talk about vulnerabilities. From a security standpoint, the absolute worst case scenario is what's known as a VM escape. This is essentially where malware breaks out of one isolated virtual machine to access data on the others. Now, thankfully, major real-world breaches like this remain extremely rare, but the threat is real. Because of this threat, and honestly, the danger of just downloading pre-infected images off the web, you literally cannot rely on the sandbox alone. A VM requires the exact same firewalls and anti-malware as a physical piece of hardware. The takeaway here, never skip your standard security controls, even for a virtual machine. Which brings us to a really fascinating architectural question. Think about it. If we can run a fully isolated OS in a tiny desktop window, what's stopping us from virtualizing your entire computer and just sending it across the network? Well, the answer to that is Virtual Desktop Infrastructure, or VDI. With VDI, your physical desk is reduced to literally just a screen and some peripherals. All the heavy computing, the memory, the storage, that actually executes on a virtual client sitting far away in a distant server rack, or the cloud. But as you might guess, there's a catch. Traditional VMs and BDs share a massive overhead flaw. Every single instance requires its own fully installed heavy guest operating system, and that eats up valuable CPU cycles and memory just to run basic background processes. It's a lot of wasted resources. So, to solve this huge overhead problem, we use containerization technologies like Docker. Instead of building separate virtual houses that each require their own heavy operating systems, containers act more like lightweight apartments. They share a single host OS. This fundamental shift makes them incredibly fast and highly portable. But as we continue to strip computing down to these incredibly lightweight remote containers in the cloud, I want to leave you with this to ponder. If all the heavy computing moves offsite, what will the personal computer of the future actually look like sitting on our physical desk?